All right, welcome class. Today we're going to be talking about solving 2x2 systems by graphing. So our focus is going to be on looking at linear systems, and we want to be able to solve a 2x2 linear systems, which means two linear equations and two variables using the graphing method. We're also going to be looking at some word problems in this set of notes today. All right, so a system is basically a group of equations that share the same variable. So in this case, you have a system of two linear equations and two variables, which consist of, in this example, we have two equations and two variables, and you can see it below, you can see it down here. So we got 3x minus 2y equals 2, x plus 2y equals 6. So in this case, my two variables are x, y. It's not limited to x, y. You can use any variables you want, but x, y is generally the one that we choose because we are graphing, and we usually do this on the Cartesian plane. And when I mean the Cartesian plane, I mean the traditional xy plane. So if you see that here, that's what I refer to. So this is the Cartesian plane, which is a traditional xy plane. All right, so the key thing to note here is that when you're looking at a system of equations, the solution is the point xy where the two lines cross. So this is the main gist of the lesson here is if you're able to graph the lines and you find out where they cross, and you have a solution. So we'll be looking at 2x2 systems of equations, which consists of, like as we said earlier, two equations with two unknowns. Now it doesn't really make too much sense to have, for example, a 2x3 system or a 3x4 system, because you need to have the same amount of equations as you have unknowns. And the reason for that is, like if you had, for example, 2x plus y plus z, and you have 2x minus 3y equals 8. Well, if you notice, this is a 2x3 system. It has three variables but two equations. So in this example, you can't really solve for z. And the point of doing a system is to solve for all the variables, which is why you want to make sure that you have three equations at least that involve the variables in some way. Okay? So yeah, in terms of systems, this is really not a good system that we want to have. So the solution to the equation is, like we said earlier, is the point of intersection. So the point where they cross, and we call that intersection when the lines are graphed in the Cartesian plane. Now, if the lines do not cross, then there simply is no solution. This only happens if the lines are parallel, which means the lines have the same slope. So if the lines are the same line, which means that the equations are the same, that means that you have infinitely many solutions since it crosses an infinite amount of points. So since it crosses everywhere, you would say infinitely many solutions. To verify whether a point xy is a solution to a system, what you need to do is you need to plug in or substitute in the values. So we're going to plug in the values and verify the both equations or more. So this should really say all equations, because it doesn't have to just be two equations, are true. So very simple to do. What you want to do is identify your x and y coordinates, which in the traditional sense x goes first and y, and then you want to go ahead and plug in the numbers into the system. So here we have x minus 3y equals -5. So we have simply 1 minus 3 times 4, plug in your values, equals -5. And for this guy, we have -2 times 1 plus 3 times 4 equals 10. And that's what we have for our system. But then just kind of doing the math here, we have 1 minus 12 is -5. And -2 plus 12 is 10. So then if we continue to do the math, 1 minus 12 is -11. which does not equal to negative 5. Negative 2 plus 12 is 10, which is equal to 10. So this one checks out, this one does not check out. So that means that this is not a solution to the system. So we say no. All right, similarly, we go ahead and plug it in for the other guys. So if we plug in x, y here, so negative 5 minus 3 times 0 equals negative 5. Well, this is just 0, so negative 5 is equal to negative 5, so that checks out. And then if we plug in the next one, negative 2 times negative 5 plus 3 times 0 equals 10. Well, this just simply goes away, and you're left with you're left with positive 10 equals positive 10, which checks out. So this is indeed a solution to the system. All right, so now we know that if we plug in points into the system, we're able to identify whether it's a solution or not, depending on whether it's true for all systems in the equation. It has to be true for every single one. So if you have a 5 by 5 system and you're plugging in for 5 variables, it has to be true for all 5 equations. All right, so now we're going to look at graphing linear equations. Well, there are a couple ways that you can solve, but we're going to focus on graphing today in this lesson. So to graph a line, there are a couple methods you can use. So you can convert the lines into slope-intercept form and use, so this would be like, say, the first method, which is, converting them to slope-intercept form, or if they're already in slope-intercept form, you can go ahead and graph it directly. So using the slope and the intercept. Okay, so this is your slope here, and then this is your y-intercept. Remember that slope is rise over run. So we're going to use the fact that slope is rise over run in order to graph the line. If the line is not in slope-intercept form and you don't want to convert it to slope-intercept form, then you can simply find the x-intercept and then solve by plugging in y equals 0. So if you want to find the x-intercept, you need to plug in y equals 0. If you want to find the y-intercept, then you need to plug in x equals 0. So plot the x and y intercepts on the graph and then connect the points to make your line. So there are pros and cons to this method. So like the cover, this is what we call a cover-up method. Now this method is simple. However, sometimes it's hard to graph the line with this method. So this is method 2, which sometimes, we kind of call that the cover-up method, because it's easy to cover up the variable by plugging in 0 and to find the other unknown. So the only bad thing is that you don't have the slope when you do this, and so therefore, it's really hard to graph more than just 2 points. So you'd have to plug in for other values in order to get more points on the graph. All right, so so this is the first problem that we're actually doing for graphing's sake. So now we have a 2 by 2 system, and we want to graph the following system. So what we want to do is we want to use one of the methods that we just mentioned. So this is not in slope-intercept form. All right, so you can convert this to slope-intercept form, or you can just find the intercepts. All right, we're just going to find the intercepts, and I can also show you how this looks like in slope-intercept form, just so that you have it for your future reference. All right, but first let's do the second method. So what we want to do is do the cover-up method. So we want to essentially, block out the 2x. So if that 2x is not there, so if we kind of just ignore that, right, then we're looking at this equation here. So negative 2y equals negative 8. All right, so then if we have negative 2y equals negative 8, then you can easily solve that by dividing by negative 2 on both sides. And so you have y equals 4. So that means our point is 0, 4 on the graph. Now, we're going to repeat that for y. So essentially we cover up y because it's 0. You plug in 0 for y, which makes that 0, which doesn't do anything. Now we have 2x equals negative 8. Divide by 2 on both sides. And so you have x equals negative 4. So your point on the graph is negative 4, 0. So that's your x-intercept. All right, pretty straightforward. So now we can go ahead and plot the points here. So now we have negative 4, 0, and 0, 4. So the purple graph is going to be the first equation. Okay, so the first equation is going to be the purple graph. All right, so now we're going to go ahead and we're going to look at the next equation. So we'll do the cover up method again. So again, cover up the x to find the y. So you can tell 2y is equal to 4. We can simply divide by 2 on both sides. So we have y equals to 2. So our point is 0, 2. All right, so now we're gonna go ahead and cover up the y. We have 2x equals 4. So divided by 2 on both sides gives me x equals 2. So we have our coordinates 2, 0. All right, we can go ahead and plot the coordinates now. So we have 2, 0 and 0, 2. All right, so we want to graph this as nicely as possible. All right, so I went ahead and graphed the lines here. So looking at the slope of the line, or looking at the point where the lines cross. So we're going to go ahead and label that point. Again, you want to do this as straight as possible in order to get the best possible graph. So in looking at the two lines, they seem to cross here at this point, which is about negative 1, 3. All right, since they cross at negative 1, 3, I like to verify that that indeed is a solution. So just to verify that it's a solution real quick, we're going to go ahead and plug it in to the original equation. So if we plug it into the original equation, we have 2 times negative 1 minus 2 times 3 equals negative 8. So this is going to be negative 2 minus 6, which is negative 8, so that checks out. And then if you plug it into the second one, 2 times negative 1 plus 2 times 3 is equal to 4. So this is going to be negative 2 plus 6, which is equal to 4, and that checks out. So that is a true statement. Both statements are true. So this is the solution to the system of equations, negative 1, 3. All right, we're going to look at another example of a system with graphing. Now this one, as I meant, going back to the other equation, I'm sorry. I mentioned that I would also show you how to do this in slope-intercept form. So if you were to do this in slope-intercept form, I'm going to show you down here how you would do that. So let me kind of isolate this for a second. So if you wanted to convert this to slope-intercept form and use that to graph, then you can do that as follows. So if you were to, I'm just going to show you for the first equation. So if you were to use method 1, what you would do is you'd have to solve for y. So you'd have to subtract by the 2x to move it over. So we have negative 2y equals negative 2x minus 8. Simply move the negative 2x in front. All right, you cannot combine those. They are not like terms. So now what we want to do is get rid of the negative 2y. So we're going to simply divide both sides by negative 2. So we have y equals, this is going to be positive 1x. And then this is going to be plus 4. So this is saying that you have a slope of 1 over 1 and a y-intercept of 4. So that means you're going to do rise 1, run 1, and then the slope-intercept of 4, or y-intercept of 4, which kind of makes sense because if you look at the graph here, this is the y-intercept of 4, and we are doing a rise 1. In this case, we're dropping 1 and going left 1. Or you can think of it as doing a rise 1 and then going right 1. So in either case, the purple graph is correct, so it matches as intended. Okay, so that's how you would use method 1 in that case. All right, whichever method you choose, you should be able to arrive at the correct solution. So let's look at the second problem. This one's already in slope-intercept form, as you can kind of tell because of the fact that it's solved for y. We have y equals mx plus b, so you can tell that the slope is negative 1 over 4. Just by looking, just by inspection, the slope is negative 1 over 4, and then the y-intercept is negative 2. So we can graph that. So I'm going to do that in purple for the first graph. For the first equation, we have negative 2. Now this means you're going to, so the negative 1 over 4 is rise over run. So you can either drop 1 and then go to the right 4, or you can go rise 1 and then to the left 4. The point is that since it's negative, you want the line to be going down, okay? So if I were to go up 1, then I would need to go left 4. So 1, 2, 3, 4, that would be a good point to choose. If I were to go down 1, then I would have to go to the right 4. And the point is that you want the line to be going down from left to right. And this matches what I was just saying. So this is correct. Now we can go ahead and do it. So the more points you have, the better. So I'm going to do a couple more points. 1, 2, 3, 4. I'm going to do one more. 1, 2, 3, 4. And the reason I simply do more points is because it's easier to draw a straight line if you have more points. I'm going to go ahead and do the other points and the other equation first before I graph it. So here we have our y-intercept is 3, so we have 3 up here. Here we have a slope of negative 3 over 2, which means you can either drop 3 and then go to the right 2, or go up 3, go to the left 2. So we're going to go up 3, 1, 2, 3, and then go to the left 2, making sure that since it's a decreasing line, it's going down. If I were to go down 3, I go to the right 2. And I'm going to do that one more time because I have a suspicion that this purple point down here is going to cross with the red. So I'm going to go down 3, 1, 2, 3, and then 1, 2. And indeed, that is correct. So they seem to cross at that point. This is why I like to do more than one point as well, because if you have the slope-intercept form, you can do a bunch of points, and then you can see exactly where they cross before you even draw the line. But just for completion, I'm going to go ahead and draw the line here. All right, I went ahead and drew the lines. So now we can tell that the lines indeed cross at the point that we were suspecting. So they cross here, which is in this case 4, negative 3. So just to make sure, I like to plug it in. So if we were to plug it in, we have, so y is negative 3. So we have, so plugging it into the first equation here, we have negative 3 equals negative 1 over 4 times 4. So we're plugging x is 4. And then minus 2. So now notice that the 4's cancel. So we're left with negative 1 minus 2, which is indeed negative 3. So that checks out. Plugging it into the next one, we have, so y is negative 3, which is equal to negative 3 over 2. Plugging it into this one. So now x is 4 plus 3. So notice that 2 goes into 4 twice. And then 2 times negative 3 is negative 6. Negative 6 plus 3 is indeed negative 3. So this checks out. So this is indeed our solution. So our solution to the equation is 4, negative 3. All right, looking at another example. This is an example where the two equations are mixed. Now what I want to do is I want to show you converting this in slope-intercept form, as well as the cover-up method. That way you're introduced to both forms, both ways of doing things. So whichever way you prefer, we can do that way. All right, so going ahead and for the first one, we want to use the method 1. So the slope here is 1 over 2, or I'm sorry, 1 over 2, invisible 1, sorry, 1 over 1. And then the y-intercept is -5. So we're going to do -5 first. We're going to do this in in purple. So -5 is down here. And then we have a rise 1 and a run of 1 here. And it's positive, which means the line is going up. So up 1 over 1. I'm going to do a few points. And I'm going to do it down as well. Okay, so now we have a nice set of points. Let's moving on to the other one. So this one, quickly do the cover-up method. So cover up the x. So then we can go ahead and divide by -2 on both sides. So we have y equal to -3. So that means we can plug y equals -3 down here. All right, and then now we can cover up the y. We have 2x equals to 6. So we can divide by 2 on both sides. So x is equal to 3. And go ahead and plug in that over here for x equals 3. All right. Like I said, the downside of this one is that with the cover-up method, you can only find 2 points. If you were to want more points, you're going to have to plug in for a different value of x and then solve. Okay. However, if you use the first method, you can get more points out of this. So that's what I'm going to show you right now. So if we were to solve this using the first method, using the first method, so let me transcribe this over here. So what we want to do is we want to solve for y, so we're going to move the 2x over to the other side. These are not like terms, so you can't combine them, so you basically write them next to each other. I like to write the x term first, and then the constant last. So now we have -2y equals the right side. Go ahead and divide by -2 on both sides. So we have y is equal to, let me erase that real quick. So y equals positive 1x minus 3. So you can see that the slope here is 1 over 1. So basically you're going up 1 over 1. So up 1 over 1, up 1 over 1, and then so on. So now you can see that you can get more points out of this. And therefore you can draw a straighter line. Now these points will eventually cross as long as they have the same, as long as they have different slopes. However, if they have the same slope, they won't cross. So if you kind of look at the graph, well, they have actually had the same slope, right? They have a slope of 1, and that's telling you that they'll never cross. So if we were to graph both lines, you'll see that they won't cross because they have the same slope. Alright, so now I went ahead and drew the lines for you guys. So looking at these two lines, you can see that they never cross. So these lines are parallel. And therefore we have no solution here. So these lines are parallel, same slope, and therefore no solution. So the good thing about, say, using the slope-intercept form is you can compare the slopes directly. So therefore, this has no solution. And this is known as an inconsistent system. So a system with a solution is known as consistent, and a solution without a solution is known as inconsistent. So this is an inconsistent system. Oh, I'm sorry, guys. I said inconsistent. This is inconsistent, and then this one I didn't even get to write it down. So if they have a solution, it's consistent. Now, if they have infinitely many solutions, such as if they're the same slope, or if they're the same equation, which we haven't seen one yet. So over here. So if we have 1 point, we have one solution, and we call this consistent. If we have the same line, which means the same equation, same everything, we have infinitely many, we call this a dependent system. And if we have, parallel lines that never cross, then we call this inconsistent, as we mentioned above. All right, pretty straightforward. Those are the three. Those are the only three possibilities if you're looking at lines. Now, if you're looking at something other than lines, then you may have multiple cases, more than three. All right, so now we're going to be looking at some applications, and we're going to be setting up the equations before we actually solve it. All right, so in the example it says you plan to work 200 hours this summer mowing lawns and babysitting. You need to make $1,300. Babysitting pays $6 per hour and lawn mowing is $8 per hour. We want to write an equation that represents the number of hours worked. So this is basically guiding us to write our system. Okay, so go ahead and go back here. All right, so we want to set up our system. So if we're working 200 hours, that means, so let's say that X is the number of hours for babysitting. And then Y is the number of hours mowing the lawn. Well, then in this case, now that we know what the variables are, we can go ahead and put them together. So since we're X number of hours is babysitting, so let's say 5 hours, and then the other, that means 195 hours have to be spent mowing the lawn. So you simply add together the hours to get a total of 200 hours. And that's our first equation for the number of hours worked. So now what we want to do for the second equation, it wants you to write an equation that represents the amount of money earned. So that means that if we're working 1 hour mowing babysitting, then we only make $6. If we're making $12, that means we babysat for 2 hours. So what we do is we multiply the number of hours worked by the amount that we make per hour. Same thing with the lawn mowing. We can multiply the number of hours spent mowing the lawn times our hourly rate. We can combine those two rates and we should get a total of $1,300 that we made according to the statement here. So that's what we need to make. And that'll tell us, these two equations together will tell us how many hours we need to work in order to meet our goal of $1,300 with these two jobs. So that now that we have our system, we can go ahead and solve this system in order to figure out how many hours we need to work in each job. So solve the system equations to figure out how many hours. So what we want to do is we want to go ahead and graph this. So we can use the cover-up method or we can use the slope-intercept method. I'm going to go ahead and use the cover-up method because that works really well for the first equation at least. So we're going to try it with both equations and see if we get the right solution. So what I want to do is I want to go ahead and cover up x for a little bit. So just imagine that if I cover up x, then I'll simply have y equal to 200. So if x is 0, y is 200. So that's this point over here. And let me just use a different color for that. Okay, so this one will be our purple equation. All right, so then if I cover up y, then that simply leaves x as 200. So pretty easy to graph. So now we have our graph. And then for the next equation, I'll do it in red. If we cover up 6x, right, then we're left with 8y equals 1300. So then we'd have to divide both sides by 8. All right, and then we're going to go ahead and divide that and see how many hours is that. But before we do that, let's go ahead and cover up the y. So if I cover up the 8y, I'm left with 6x equals 1300. And go ahead and divide by 6 on both sides. And so x is equal to 1300 over 6. So then we're going to go ahead and compute these as decimals. All right, we plug it in the calculator, so we get 162.5 hours. I'm sorry, so 162.5 for y. Yeah, 162.5 hours for y, 260.7 hours for x. If we're not, if we're solving for just x and y alone. So then if we have 162.5, this is about 175 over here. So 162 would be, somewhere around here. This is 175. So this has to be about so 160 should be around here, 162. So I'll do it around here. And then for that actually should be for the x, I apologize. So for the x is 216.7. So that means this is 225 over here. So it should be pretty close to it. So if this is 225 over here, that means 216 should be around there. And then 162.5. So this is about 175. So 162 be around there. All right. And now we can go ahead and graph the lines and then figure out where they cross. All right, so I went ahead and graphed the lines. So also note that I made a slight error in labeling the axis here, since I said that x was lawn mowing. This right here the y-axis should not say babysitting. So right here, we said that y was the lawn mowing. So this was the lawn. So just make sure you make that adjustment. So this is for the lawn. And we said that, so we said that y was the lawn and x was the babysitting. So simply swap the labels. But looking at the graph, it seems to be that this is my point of intersection just by looking at it. So this is about 150, 50. So that means x is 150, y is 50, and we want to verify that this is indeed true. So we plug it in to the original. So this kind of makes sense because 150 plus 50 is 200. So that's what we were looking for. We were only looking to work 200 hours in the summer. And if we plug in 6 times 150 plus 8 times 50, you will make $1,300. So this is the solution that meets both criteria. And so this is our final answer. So mowing the lawns is, in this case, it's y, our y coordinate. So we want 50 hours mowing the lawn, and we want to do 150 hours of babysitting. And this will provide the right criteria to, in order to meet 200 hours and make $1,300. All right, so then we're going to look at one more problem. So we're looking at reefs. We're making small reefs and large reefs. The small ones sell for $8 and the large ones sell for $12. You want to sell 40 and you want to make $400 off of this. How many of each should you make? So again, using the same equation, we're using the equations, let's make x equal to the number of small reefs. So the number of the small reefs, and let's let y equal to the number of the large reefs. So in this system, we want to make 40 of them. We want to sell 40 of them. So that means x plus y is 40, and we want to make $400 off of it. But the number of small ones sell for 8, so 8 times x, and then the large ones sell for 12, so 12 times y. Put them together, you get $400. So that's our equation. We want to go ahead and graph this. So if we cover up x, we get y is 40, so we can simply graph that over here. And if we cover y, x is 40, so we have that here. So this is the purple. And then for the next one, if we cover up x, we get 12y equals 40, or 400, divided by 12 on both sides, and that'll give us y. If we cover up the y, we have 8x equals 400, divided by 8 on both sides, so it cancels. X is 400 divided by 8. This is going to give us 50, so that'll be a nice number, 8 times 5. All right, 400 divided by 12 will probably give us a decimal, so I'm going to go ahead and calculate that. All right, guys, so I want to go ahead and calculate what y is. So if you look at the y, we got 33.33, and if we look at the two equations or two lines, they look to cross around here. So it looks like at about 2020. So then if we want to go ahead and plug this in, 20 plus 20 is 40, so that checks out. And if we plugged it in here, so we have 8 times 20 plus 12 times 20 equals 400. And if you check on that on the calculator, it does check out. So this is the solution to the equation, to the system of equations. So if we sell 20 small reefs and 20 large reefs, we'll make exactly what we want. All right, guys, that's it for the lesson. I hope you learned something from this, and I will see you guys next time.